Hey everybody. So I got a couple of questions about the cycloid from the parametric equations material, and so I wanted to go through a little bit of how that's derived, and I also just want to point out that while the cycloid is important, there are plenty of applications and interesting things about this. It's not particularly important to us. It's just a good example, right? It's a good process for thinking of how we can how to think about these parametric equations and how to construct them and those kinds of things. So let's set up what's happening. So what I've got here is a picture of we've got a wheel with radius a. Let's put its center in. It's moving to the right. Oops. All right, so there's the center a little while later. So you got to imagine this thing rolling, right? It's going to be rolling in this direction. Okay, so I've drawn it at 3 different moments in time. And what we want to imagine is a point that starts, maybe we draw a little red dot on the side of this wheel, and we want to imagine what's going to happen as this wheel rolls forward. Okay, so it's a little hard to imagine, but that point that's at the bottom, the first thing it's going to do is move straight up. Right, as this rolls forward, it's going to go up and start to move forward. So I'm going to freehand this, but if we imagine, let's say, and I didn't measure this, but if the distance from, let's do this in black, if the distance from here to here is half the circumference, in other words, we're doing half of a rotation, or that would be pi times a, well, this red dot's going to end up on top, right? We've turned it around halfway because this distance we roll is equivalent to how much of the wheel touches the ground as we roll, right? So by the time we go half a rotation, we should end up there. And when we fully rotate, we should end up back where we started, except there's also this forward motion. So we'll talk about that in a second. And the path is going to look something like this. Let's see. Let me try it one more time. I think it should be a little more like that. And then this side's harder for me to draw for some reason. It gets a little wobbly. Okay, doesn't need to be perfect. That's the idea. And then of course it's going to repeat. So going off in that direction as the wheel continues to roll. And had the wheel been rolling from over there, it would have continued to roll. So what we're going to try to do is come up with a set of parametric equations where we imagine this now living on a coordinate axis. So let's say that this line I have in here is the x-axis, and I could throw a y-axis in anywhere I want, but I'm going to throw it in so that the origin is right at one point where that little red dot is on the ground, is at the lowest point of the circle, right? So those are choices I'm making. We could have put the x-axis through the center and the y-axis when the dot was on the right or the left or anywhere else. This is the choice I'm making, right? So oftentimes when we parameterize things, there's plenty of choices to be made. So you notice the language is often a parameterization of this shape, not the parameterization, because there's different ways to parameterize different things. Okay, so there are a couple of things going on simultaneously with this dot, okay? So for instance, we want to separate into the 2 different things that are happening. There's a rotation happening as it rolls around the circle, and then there's this forward motion as the circle goes forward. Right, so one way to separate them, or at least this works for me, is imagine there's a camera attached to this wheel, and as it rolls, the camera's just moving with it, right? All you would see is the dot going around, because all that forward motion is with the camera, so there's no, you're not seeing that, right? Imagine you're on the highway looking at a car next to you. You can see its tires spinning, even though they're moving forward because you're moving with it. You don't see that motion the same way, right? So there's that motion of spinning around and around and around. And then there's also this added motion of moving forward. And so we're going to think about this by separating those two motions out. All right. So let's start with the rotational motion. Okay. So we want to rotational motion of this point. So if you were on this camera tracking this wheel as it moved, right? This dot, let's do it right here. Lives on a circle with radius A. We want it to start at the bottom. And remember, the wheel is spinning this way, so it's going to move in the clockwise direction, right? It's rolling forward, so it's moving to the right in the way I've drawn it. And so it's going to be rolling in a clockwise direction. So that's what we want to write down first. We'll deal with the forward motion a little later. Okay, so let's just start picking apart this idea. So you might remember from trigonometry, right, that the definition of sines and cosines have to do with the circle, right? If we have a unit circle, just doing a quick sketch, unit circle, and there's a point on the circle, there's an angle. Oops, I missed my point. Let's just move the point to there. We've got this angle. Let's call the angle t. That the point right here has coordinates cosine t, sine t. And in the way the definitions of sine and cosine are constructed, positive angles move around in the counterclockwise rotation. Okay, so you have to remember a little bit of this trig stuff. So a very basic idea from this is that we can parameterize motion around a circle in a counterclockwise direction with the following parametric equations. I'm going to call these, I'm going to put a little asterisk on them because we're going to be kind of changing them as we go. Okay, so I'm just sort of using that to mean like in progress. So I've got y star and x star of t look like this. This will give us a circle. Well, let's add a graph here. Maybe we'll use this as an opportunity to remind ourselves of a few different things. So I'm going to sketch the graphs of sine and cosine. So let's get ourselves one period. So out to 2 pi. Put pi in the middle. There's pi over 2, 3 pi over 2. So I'll do cosine in blue. Cosine starts at its peak. By pi over 2, it's at 0. By negative pi, let's try to be a little consistent. Then we go back to 0, and then back up to the peak here. So the shape looks something. Again, I'm drawing these freehand. They're not going to be perfect, but they're just to give us an idea of what's going on. It looks a little smashed, but we'll deal with it. Sine, on the other hand, starts at 0. When the input is 0, it hits its peak at pi over 2. It's back to 0 here. Hits its minimum, and then back to 0. And so it looks something like this. Okay, so I've drawn one period of these two things, and this will be enough to help us out here. So let's think about what, in terms of parametric equations, what happens here. If we're at, let's give ourselves a drawing to work on, yet another circle. Yeah, on the coordinate system. So remember, we're just concerned with the rotational motion right now. I'm going to draw a circle as a guide, but we're really just thinking about a point. Let's try to center that a little bit. Okay, so if we've got this, the parametric equations we have right now, okay, and let's say that this circle has a radius of A, like the one that we want. So I'm just parting this one point in, right? So at t equals 0, cosine of 0 will be 1. I'm looking at the blue graph here. So our x coordinate will be 1, and our sine will be 0, right? So let's pretend A is bigger than 1. That means right now we're in here, and so I already know things are off. So let's immediately realize, all right, we need to push this thing larger or smaller. Maybe A is less than 1. I'm just going to assume it's larger for the time being. But either way, we can scale this thing by A. Okay, so all that does to these graphs is stretches them vertically, and I can just change my coordinate system. Oops, I wrote that wrong. That should be not 1, 0, 0, should have been 0, 1. Now 0, A. Okay, so that's how high we're starting, right? Okay, so now we've got a circle. Now we're starting right here. And let's just think about what happens, right? So this point is representing what we have the output for our parametric equations as written. At 0, we start right here because we can look at this graph and see the x. The blue line is representing the x coordinate. It's the cosine, and the red is the sine. We're at the output of the blue line is A. The output of the red line is 0. So we start at A 0. As t increases, what happens? Our x coordinate, the blue line, starts to decrease, right? So it's going to move leftward, while the red line increases. Well, increasing and moving left means we're going around the circle like this. Okay, so I'm not going to completely review the trig stuff, but that should give you a little hint of what's happening. This is giving us a circle. The lines we have right now is beginning at A 0 and go counterclockwise. Okay, so we've got circular motion, but it's not the circular motion we want, right? Let's remember what we want. We want to start at the bottom of the circle and move clockwise. So that's what I should write this in. I wrote it in a picture. Begin at bottom, move clockwise. Okay. Well, luckily, all we have to do is mess with these parametric equations and these two trig functions. It's going to be something very similar to this. Let's just try something without even worrying about what's going to happen. It'll start giving us some intuitions, perhaps. Just get some extra practice with these. What if I were to just switch and make x equal to a sine t and y equal to a cosine t? Okay. Well, now at 0, the x coordinate is 0 and the y coordinate is a. So that means we would now be starting at 0a. We're at the top of our circle, which is not what we wanted. But what's going to happen immediately if we as we increase t, remember now the x coordinate is defined by sine, the red graph. If we increase t, sine begins to increase. Our x coordinate increases, so we're moving to the right, but our y coordinate decreases, so we're going to the right and down. We're moving clockwise. So here we've got one moving clockwise, but it's starting at the top of our circle. Okay, so it's still not quite what we want. Let's make a little space somehow. We can move down a little bit. This is all right. We'll be able to still see this. So let's try a different configuration. Okay, because remember, we want to start at the bottom of the circle. So one thing I could do is I could just, if the bottom of our circle would be at 0, negative a. So maybe I try just putting a negative on here, right? It certainly starts where we want now. We're at the bottom. Right, we're at the bottom. It's starting where we want. Let's see what happens when we let t increase. Okay, so again, my x coordinate is given by the red graph now. It's defined as the sine. It's going to start increasing, so I'm moving up. Y of t is now a negative cosine graph. So I have to think about this blue graph, but flip it upside down, right? That's what negative cosine would look like. I'll do this one dotted. It's going to look, it's an inverted version of that cosine graph. Okay, so notice as we start to increase t, the x coordinate is going to increase, meaning it's moving to the right, and the y coordinate is also going to increase, meaning moving up, because this dotted cosine graph, which is the negative cosine, is increasing, which means, so we're moving to the right and up. This is moving counterclockwise, right? So now we've got one that's starting at the bottom where we want, but it's moving counterclockwise, right? And I know that it feels right now like I'm just taking guesses, and I really am. Sometimes it's just fine to play with this. We're getting an idea for how these functions work, right? I know that sines and cosines are going to live on the circle because that's that's how they're defined. They come from circles, right? That's a good definition of them. And so I'm just playing around with them to see what happens. And now I've got some good intuition. Look at what's going on. Right now, I've got my y coordinate increasing. If I was to move clockwise, the way I want to be going from the bottom, what I want is the y coordinate to increase, but the x coordinate to decrease, okay? So right now it's increasing, but what if I were to add a negative to it? I'm going to leave this one alone. Okay, so now I'm going to have a reverse sine graph, a flipped sine graph. So that's going to look like this. Okay, let's clear some of this other stuff out. All right, let's get rid of the originals. So now here's our two graphs. The red is still the sine graph, and the blue is the cosine, except they're both flipped. So let's think about what's going to happen. At the beginning, sine of 0 is still 0, so the negative doesn't matter. We're still beginning with an x coordinate of 0. Cosine of 0 is 1. We've got this negative a in front, so we're beginning at the bottom of the circle. That's perfect. That's what we wanted. As t increases, so we're starting at 0, what happens to our x coordinate? The x coordinate is given by this red dotted graph. The x coordinate immediately starts decreasing, moving left. Okay, so our point starts moving left. The y coordinate given by this blue dotted graph increases, starts moving up, and that's going to be the clockwise direction. Okay, so now we have functions, parametric functions, that describe a circle, a particle moving in a circle. So let's write this here. Our parametric functions so far. We have x star of t is equal to negative a sine of t, and y star of t is negative a cosine of t. So these are describing motion of a particle beginning at 0, negative a. So begin at, if the beginning is at t equals 0. And then moving clockwise. Okay, so now we've got what we want. If we were traveling along with that wheel, we would see this. It's hard for me to figure out which way to do this in the camera, but imagine a circle, a particle rotating clockwise. Okay, so now we want to add in the other motion, the fact that it's on a wheel moving to the right. So there's a couple of things. What we're really doing, right, let's say it this way. These parametric equations describes a particle beginning at 0, negative a. Like we have this origin, and we're rotating around that origin. We want to change this origin, or we want to change the point that it's rotating around. Remember our picture. In fact, let's bring this picture down. We're not rotating around the origin. We're moving past the origin. The point we're rotating around is above the x-axis, and it's moving to the right. So we'll want this picture down here for the next part. All right. Right, so now we need to change the idea that we're rotating around a static point at the origin and say we're rotating around a point that's up and moving to the right. Okay, so let's do the easy part first. Let's move this circle up, right? Well, how far up does it need to move? It just needs to be up by the radius, right? In other words, every y coordinate, so now instead of, we're still not moving, instead of having a circle rotating around the origin, we just want to move this circle up. What happens if we were rotating around this circle? We just want to move up to this circle. We just have to take every y coordinate and move it up by a radius. In other words, our new, so we'll move, let's use a more mathematical term, shift. We'll have a vertical shift by positive a units, which is just going to be, so I'll call this y of t. This is going to be our final, this is going to give us exactly what we want. We're going to take a positive a and add it to that rotating motion, right? So think about what this does. It spits out all the same y coordinates, except each one is moved up by a units, right? So whatever the x coordinates are doing, the same thing is still happening, but all the y coordinates are moved up. So the circle moves up. And so if we put in what we had, y star was negative a cosine of t. So we've got a minus a cosine of t, or if we want, we can factor it and get 1 minus cosine of t. All right, so there's 1/2 of our parametric equations. That will handle the y coordinate. It'll make sure it's spitting out the values along this line that we've drawn here. Right, so for instance, when, well, we'll come back to checking some points. Let's get them both done first. Okay, so now let's do the harder part. We want to move, we want this center of the circle to now be moving to the right. Right now the center is at 0. Our center now we've shifted it up. It's at 0a, and we're rotating around, but we need to move it. Okay, so particle, how do we get the horizontal motion? Let's say this. So I'm not sure if I said this clearly, but part of what's going on here is that this circle is rotating at a constant speed. Okay, so it moves right at constant speed. So how do we figure out how fast? Well, let's think about it this way. So let's do a little drawing. All right, here's our wheel. There's where our particle is in the beginning, okay? So let's say a little while later, our wheel has moved, right, in the clockwise direction. It will have moved across, but I'm just drawing it in the same place. This angle is t, right? T is playing the role of our angle, right? Well, how far has it moved in time t? Right? In other words, what's the length? Let's get this out of here. What's the length of this arc? Right, I'll call this L. Maybe you remember your trig, maybe you don't, but we can certainly figure it out. So let's just use proportions, perhaps. T is some portion of the circle, right? It's some portion of an angle all the way around the circle. We know that all the way around the circle is 2 pi. And we've gone t of them, right? So if we go pi over 4, then we've gone 1/8 of the way around. Or if we have pi, we've gone halfway around, right? So this is the proportion around the circle. Well, L should be the same proportion of the circumference, which we know to be 2 pi times the radius, which we have called A. Okay. Remember, we wanted to know this length. How far have we moved in time t? Okay. Well, we've moved. Let's just solve this for t. The 2 pi's cancel. We multiply by A. The amount of length we've moved in time t is A times t. Right? The radius times how long we've been traveling, right? This is also from trigonometry, how we define radians, right? Radians are defined as the arc length over the radius, right? So for an angle, you look at how much of an arc it subtends on the circle and divide it by the radius. That gives you the angle. We've just manipulated that equation, okay? So that tells us how far it should move per unit time, right? For every unit of time it moves, this is this radius is actually giving us our velocity here. Okay, so this is like a position function. For time t, L is how far we will have moved, right? Because the amount of curve around the circle we rotate will equate to how much ground is kind of pushed past, okay? So if we start at 0 and travel for t seconds or minutes, whatever our units are here, will be a distance of AT to the right. We need to add, we need to shift horizontally. These 2 L's look funny to me. I'm just going to leave it. Shift horizontally positive AT units. Right? It's changing. So in the beginning, when t is 0, we're not shifting right at all. When t is equal to 1, we'll be 1 radius over. When t is equal to 1,000, we'll be 1,000 radiuses over to the right. That's how much we're moving. So what that tells me is that my horizontal coordinate will be the original coordinate, right, from the rotational motion that we came up with before. Let's actually write it out as x star. That was what we called x star of t. And we want to add in this motion to the right. Okay, so we're just adding these 2 motions together. The x star is just rotating around, but then at each point, we're just adding a little shift, right? So it starts moving in this direction, and wherever we're at on that circle will be that much further to the right. And so if we write this out, it looks like x equals AT minus a sine t, or x of t is equal to a t minus sine t. Okay, so far so good. This should be our these should be our parametric equations for the cycloid. This is a particular parameterization, right? We made some assumptions in here. For instance, we took this speed to kind of be the simplest version. We could speed this thing up by multiplying things, the input t. And if we multiply it, then we imagine a circle spinning faster or slower. But this is a pretty straightforward parameterization. Let's convince ourselves this is correct, at least a little bit. Let's just check it at a couple of points. We'll try it at 2 points. First of all, let's take a look at y of 0, x of 0. Let's do it in the more traditional order, x and y. X of 0, y of 0 gives us the point. So x of 0, we get a times 0 minus sine of 0. Sine of 0 is 0. This whole thing's 0. Gives us 0. And y of 0 is a times 1 minus cosine of 0. Cosine of 0 is 1, so that's 1 minus 1 is 0. We get 0, 0, and that's exactly where we wanted to start, at the origin. Okay. Let's take a look at t equals pi, right? This should be a half a rotation, right? The way we've set this up is each unit time is a unit of radian angle measure. So at pi, that should be when we're at the top of the circle, right? This is t. T has traversed pi units, okay? So let's look at x of pi. That's a time. Oh, let's decide where we should be at this point. So this horizontal axis, I guess. Sorry, I had a little technical issue, so there might be a little jump there. So what was I saying? All right. Half a rotation is when t is equal to pi. We expect after half a rotation, the distance our x coordinate will change. Like, I guess I'm just repeating that. What we put up there is pi times a. So this point should have an x coordinate of pi a. And the height is 2 radius, the diameter, 2a. So let's see if our parametric equations spit that out. So putting pi into the x coordinate, I get a times pi minus sine of pi. Sine of pi is 0. So I get a pi, or pi times a. I don't know why I like it written that way better, but I do for some reason. And then our y coordinate at pi is a times 1 minus cosine of pi. Cosine of pi is -1. So we get 1 minus -1, or 2, gives us 2a. And so we get exactly what we anticipated at these 2 points. This, of course, doesn't prove this is correct, right? This just tells us that at least we haven't shown us that we're definitely wrong. I'll leave it up to you if you want to check a couple of points, like maybe the next point it hits the x-axis there. You could also move in the opposite direction and it works out. And so that's one parameterization of the cycloid. You can certainly do other ones. You could do ones with sines and cosines. In the original, x is a cosine of t and y is a sine of t, but do some phase shifting in there. I'll let you think about that, some other kinds of transformations. This one was the easiest way for me to think through it. But like I said, there's other ways to do it. Okay, that's it for this. Thanks, everybody. See you next time.